Departing from the soft issues, something that is easy to do remotely because it only requires a computer, let's switch to hardware. So from software to hardware, Angelika Tefelska, Dr. Angelika Tefelska, also representing the physics department of the Warsaw Technical University, will tell us about how to teach electronics remotely if you have appropriate hardware. Over to you. Right. Welcome, everyone. Like Darek said, I will tell you about our experience in teaching electronics and microcontrollers at the Department of Physics during the pandemic. This lecture is going to talk about what seemed impossible to us at first, because how can you teach something that requires hardware without being in touch with that hardware remotely? And after 2 semesters, it became a real possibility, teaching electronics without having access to a fully developed lab or without being in face-to-face contact with the lecturer. But let's start with a quick question to you. Do you know where this photo was taken? In what city was it taken? Any ideas? I hear China. Yes, very good. What's the most famous city in China? Wuhan. Yes, now it's Wuhan. So a quick trip to 2019 when in Wuhan, this is a yellow crane tower in Wuhan. Wuhan became a famous city in 2019, not because they have excellent universities, you know, all European universities brought together would be smaller than Wuhan University, but it's not because of their universities or industry. It wasn't because in November 2019 they organized a number of different conferences as they did, but it's because it was exactly there where the pandemic started. We were not prepared for that. We never thought that we will have to wear masks and go back home and just do our education remotely. To be honest, in November 2019, I was in Wuhan. When I was using the metro, I thought, you know, it would be excellent if students, where they get sick, come to the lectures wearing masks without passing the infection on to us. So it was a self-fulfilling prophecy. You know, back then, masks seemed so wonderful. So now, going back to our topic, in truth, the start of the pandemic caused one essential thing. Without prior notice, we were sent to remote education. You know, overnight, we were told, you teach remotely tomorrow without any preparation. Nobody supported us, told us how to do that. We could use MS Teams, but other than that, nothing. So how do we adapt our materials? Nobody told us, nobody trained us. Overnight, we had to wake up in the new reality and handle it. So theoretical topics, yes, it's imaginable, but what to do if you need a lab? How do you do these classes? The first semester that started right after the pandemic started was the worst semester possible because we had to do all that basing on simulators. We had 2 courses back then. One was in analog electronics, level 2. It's called Electronics in a Physical Experiment. Luckily, these were experienced students, experienced with electronics, so they already had previous 6 months of contact with electronics. The other course was focusing on microprocessors, teaching about AVR-AT Mega 30 microprocessors. We based our teaching on 2 simulators. Multi-sim, that's the first one. It's a simulator where you can do all kinds of measurements. It looks more or less like this. So you can open a panel, LV panel, and the students had it in the lab, and on the simulator it looked as though they were watching the simulator live, only you were organizing the elements, you know, like pulling on the resistor or the condensators, and you were binding specific elements with proper cables marked as oscilloscopes or Bode's analyzers. And on a simulator, you could do measurements. This is an example of characteristics of a frequency function for one of the systems, so students could download that and analyze this data. Our experience was that if a student was previous experience with electronics, it wasn't so bad to work on a simulator. They could learn additionally about the simulator if certain things were possible to be simulated, because these simulators do have their limitations as well. So it's not perfect that all classes could be conducted this way. Now, teaching about microprocessors. We were assisted by a free-of-charge simulator, Similide. That's what it's called. It's a list of available microprocessors. You can pull one from the list. You can use all kinds of components that can be pulled out from the list. This is an example of a LED matrix. You can input a program, a software you write into that microprocessor. The benefit from this simulator is that the same code that you would write for a real-life equipment is going to work on the simulator in exactly the same way. So you don't have to add any extra elements that would sort of detract from the learning process. So after this first semester, we decided that that semester, well, it was well as it was. It wasn't perfect. Not all aspects were possible to be executed, especially when it comes to microprocessors. The limitations of the simulator were such that half of the curriculum was not executed. So we had to continue through the next semester. So instead of having a single semester course, they had a two-semester course, which was a burden and a challenge. And so then we came up with an idea that we had to streamline things a little bit. So how to do that? The entire electronics lab, where we have all kinds of equipment needed to do measurements, generators, oscilloscopes, and how do we put all that in a tiny little box that we can give to a student to work on that remotely? And it turns out that one of the manufacturers created a piece of equipment like that, a device that can fit into your hand. You can put it, you can link it with a computer, and it stands in the three. So it supplements the three separate devices. You can do all kinds of practice runs of electronics on this. So our dean managed to finance the purchase of 80 such small boxes, such small devices, and we distributed that to the students at the beginning of the semester. So the students came, borrowed, and then returned after the semester these devices. So this is the box that we issued to the students. It included all kinds of components, analog discovery, amperometer, all kinds of elements like resistors, potentiometers, and so on. And semiconductors, also all kinds of cables. And at home, they could execute all the measurements as if they were doing them in the lab, only they were not linking up to an oscilloscope, for instance, but to analog discoverer, then to the computer, and on the computer they were analyzing data. So for all that to go smoothly, we realized that we couldn't just leave the instructions as they were with electronic schematics and hoping that the student would know how to put it all together, because they wouldn't. So we had to modify our instructions, make them more user-friendly. So everything that you had to put together was clearly illustrated, and we were assisted with fritzing. That's the kind of software that allows you to do that kind of schematics. So you've got analog discovery board, all the elements that have to be linked together. You see how to do that exactly, and this made things much easier to the student, much simpler than being left alone with it. On the next step, the dedicated software was used for analog discovery, and you see that it contains all kinds of instruments. So you choose scope, like an oscilloscope or other devices. Depending on what you choose, you either get a configuration window to choose what you wanted to generate, or just a single window that shows you the course of what's happening on the screen. When it comes to microprocessors, we used the exact same principle, only this time we had to find a board that would include all the components linked together, so we can focus on the software creation part rather than electronics itself. And so we purchased such boards where you've got a microprocessor here and all the subunits are added to it. This is a Polish manufacturer as opposed to Analog Discovery. So, but it made it possible to do all kinds of courses with microprocessors. We purchased additionally some elements like the engine, and so that the students could work with these elements as well, and it all worked out really well. So what were our conclusions after semester 2 of such remote teaching? First of all, we noticed that the level of skill of students, both when it comes to electronics and microprocessing, was comparable to that of students prior to the pandemic, which was quite an accomplishment from our point of view. But one thing happened that surprised us. First of all, weaker students, handled the course better than they would during face-to-face teaching. Why? Because normally they would come to the lab, they have 3 hours. If they didn't do the measurements they were intended to do, then, well, that's a shame. You're up, your time is up, and you have to go home. At home, you still have the equipment on you. So even if you don't fit into the appropriate time, you can do more measurements later, and you can catch up with what you didn't do over the 3 hours. So this was a plus. The other surprising thing was that during microprocessors class, at the end of the semester, typically we would have an additional project to improve your grade. Typically for 8 students, 2 or 3 in a group would go for it. This time, nearly everyone did it. 100% of students wanted to go for the extra credit project. So it was amazing. They wanted to devote their own time, come up with their own project and do it at home. And this was another thing that truly surprised us. The fact that they could, at home, without stress, after class, do some sort of project. It motivated them to do the job, to do the work. And it turns out that remote learning at first seemed like a tragedy to us, something completely impossible. How can we teach electronics and microprocessors at home? But it turned out to be an excellent solution. It turned out that we have obtained the results that were sometimes better than with face-to-face training, which doesn't mean that we should close down the university, but it shows you that you can teach electronics and microprocessors without being physically present in the lab. In truth, during the pandemic, we realized one thing. This approach is all good and well if the department endows you financially and provides for this equipment. Unfortunately, after consulting with other universities, we found out that we were an exception to the rule, because we were able to purchase these devices, rent them out to the students. The majority, unfortunately, focused on simulators. Or they bend the rules and met with the students face-to-face, even though there was a ban in place. And then we realized that we could do a project. It's called Engine. It's an Erasmus Plus project focused on adapting educational materials in such a way that those universities that could not afford new electronic devices could still do their courses, perhaps less efficiently, but still at a satisfactory level. And we wanted to create the kind of materials that would support teachers and lecturers in organizing remote classes, remote studies, because just telling them, oh, go and teach remotely is not a good approach, because not everyone knows how to go about it. So you have to come up with some innovative methods of doing remote teaching. What do you need to change to make sure that the student is not just going to fall asleep or play a game on a next screen? So how do you get involved and get the student involved? This project we co-organized with the with different universities and institutions representing 3 countries other than Poland. It was Greece and Italy. And together we created a platform called Moodle, where we provide free of charge courses divided into 3 categories. Category 1 is electronics, then microprocessors and coding. So this is where you can find these materials. If you think university courses are not for pupils, that's not true. Many of these things can be adapted and used in earlier education, especially when it comes to coding. There are some elements that are already done at schools, so you can adapt that too. And now, how were these courses divided? First, we thought that it wouldn't make any sense to create too many courses, because the drawback, or for instance, Udemy or Coursera, well, first of all, these are paid courses, but also there are so many that a student feels overwhelmed. So, you know, there is no order. You don't know what to do when you graduate from one course, or, you know, this one is too difficult for you, don't go for it, start with something else. So we focus on a small, limited number of courses, but courses that are logically associated with one another. So we had 2 courses in electronics, basics of electronics, that's basic level, level 1, where we explain the foundations, and then we go to a more application-focused part of analog electronics. That when it comes to programming, we started with a course focused on Arduino. It's a board that seems to be simplest for the users that do not know much about microcontrollers. Then on the intermediate level, you can go through one of 2 courses. One is based on a microchip, the other one on a microprocessor from the AVR family. And for people who already feel more certain, more confident in various platforms, equipment platforms, we recommend an advanced course on ARM microcontrollers. Now, and programming courses were divided in a similar way. So the most user-friendly language is Python, so we recommended to start with that. We've got 1 course in Python. Then we recommend to switch to the C language, or rather an abridged version that is needed for microcontroller programming. So not all aspects of C language, but what is effectively needed to program the equipment without going much into the detail. And then if you are more interested in objects, then we have a course that focuses on C++. And then depending on which courses you did go through, you can go to a more advanced level hardware implementation. And all these courses have been prepared on simulators, on 4 kinds of simulators. The first one is LT Spice that was used to teach electronics, since that's a simulator available free of charge and relatively simple in use. Then Arduino was used on Tinkercad simulator, and then we go on. Microcontrollers were done on Prometheus, and microcontrollers AVR were done on Simulide that I presented before. Now, about programming languages, we focused on selecting a single platform that would be adequate for all languages, and we can use that platform to program without configuring the environment on your computer. So we selected Google Colab Research, where you can write both in Python, C, C++, so it's not much of a problem. This is an example of a program that was written in C++, and it looks like a notebook. So at first you can add a section with a theoretical description, then a file where you put a bit of a code, and then some shell commands where you can compile a bit of a code, and instantly you see the result at the very bottom. So it's a very comfortable environment, because you can put bits in, you can give examples on the board, sort of, and tell the students, check this and this element and check what happens. So this doesn't require things being created from scratch. You can configure them and see what happens. And to summarize, I would like to say that in general we notice two things. Students obtain optimum results if they are in physical contact with the equipment, even if it's a rented out set or kit. You can use boards like Analog Discovery, replacing a lab, an electronics lab for us, in a limited scope. Of course, it's not a kind of board that would offer perfect precision, but it's enough to do classes in electronics for students. Students are more involved in the course if they have real equipment on their desks. They can use it whenever they want in the middle of the day, not just during classes. When it comes to universities without access to such equipment, not able to purchase it for financial reasons, we encourage them to use the engine project results. So a platform offering free of charge online courses. You can employ them, adapt them to the given university. Students can use them for self-training, and even pupils, younger pupils, can use them to start their adventure with engineering topics, programming, or electronics. Thank you very much for your attention. Thank you for your presentation. One thing that puzzled me, 80 kits. This costs 2,000. Now it costs 2,000, but before the pandemic, if you had a student discount, it cost 1,000, and the cost of these kits together was 1,500 zlotys. So over 100,000 zlotys. The dean was really generous. For 80,000, it ensured good level of education. This is a sad comment, unfortunately. Education costs money. Sometimes there is no way around it. So without appropriate resources, it's just going to be tough. So once again, congratulations, and excellent that we can do it, that we've got these opportunities. If people want to do something, if you tell someone to do this now, right now, no, now sit quietly, now listen to me, and so on. If you tell that to someone, that's exhausting. But if you provide blocks to a small child, they are going to play with it for hours. And the same happens if you give an appropriate device to a student. They will play with it for hours. So I hope that you have those projects that you really want to execute because you want to do them.